UC Irvine discover revolutionary new state of quantum matter. What if your computer could power itself forever and survive the brutal radiation of deep space? A team at UC Irvine just cracked a quantum mystery that might make this possible. But here's where it gets controversial. This breakthrough isn't just about better gadgets. It could redefine how we think about matter itself. Let's dive into the science behind this discovery and why it's causing so much buzz in the physics world. Imagine a material that behaves like a glowing, liquid-like substance made of electrons and their missing partners called holes. This isn't science fiction. It's the new quantum state discovered by UC Irvine researchers. When exposed to an intense 70 Tesla magnetic field that's 700 times stronger than a typical fridge magnet. This is a phase of matter we've only theorized about until now. The implications are staggering. Unlike today's electronics which degrade under cosmic radiation, this material could create computers that never lose power and function flawlessly in space. We're talking about a complete paradigm shift, Jauregui adds. Instead of moving electrical charge, we're harnessing electron spin to transmit signals, like swapping horse-drawn carriages for electric trains. And this is the part most people miss. The material's resilience isn't just about surviving radiation. It could enable spin-based electronics that use 100 times less energy than current systems. Picture Mars rovers with batteries that last decades, or satellites that never need maintenance. But here's the twist. Will this technology remain in labs, or can we scale it for real-world use? Jauregui's team is already grappling with that question as they explore how to stabilize the material outside extreme magnetic fields. The breakthrough emerged from a collaboration between UC Irvine and Los Alamos National Laboratory. Postdoc Jinyu Liu synthesized the material, hafnium pentatelluride, while graduate students and undergrads contributed to device fabrication. Theoretical modeling by Lanlell researchers revealed how the magnetic fields force electrons into this exotic state. It's like watching a caterpillar turn into a butterfly, says co-author Shizang Lin. We're witnessing the birth of a new quantum phase in real time. So, what's next? While the team celebrates this first-of-its-kind measurement, they're quick to note the challenges. We don't yet know what other surprises this material holds, Jauregui admits. Could this be the key to sustainable space exploration, or are we overlooking fundamental limitations? We'd love to hear your thoughts. Drop a comment below and share your predictions about where this quantum leap might take us. Quantum breakthrough, exotic matter for space missions. Imagine a world where space computers hum with power even as cosmic radiation tears through them. Sounds like science fiction, right? But here's where it gets wild. Researchers at UC Irvine just uncovered a quantum material that could turn this dream into reality. This breakthrough isn't just about abstract physics. It's the first real-world proof of a predicted quantum state that defies classical understanding. Let's dive into how this works, why it matters, and the space-age implications that could leave traditional semiconductors in the dust. Revolutionary quantum state of matter, radiation-proof self-charging computers. Imagine a future where computers not only power themselves, but can also withstand the harsh radiation of outer space. That's the groundbreaking potential of a newly discovered quantum state of matter called the Spin-Triplet excitonic insulator. This isn't just theoretical. Scientists have finally observed it in the lab. Dr. Alfredo Carpenetti, with a PhD in astrophysics and a master's in quantum fields and fundamental forces, sheds light on this revolutionary discovery. He explains that traditional electronics rely on semiconductors, which involve electrons and positively charged electron holes. These components can sometimes form excitons, bound pairs of electrons and holes. Under specific conditions, these excitons can even organize into excitonic insulators, where they move collectively without conducting electricity. For a long time, the only known type of excitonic insulator was the spin-singlet variety, where the electron and hole had opposite spins. However, the recently discovered spin-triplet excitonic insulator is different. In this state, the electron and hole spin in the same direction, marking a significant departure from what was previously understood. According to Professor Louis Jauregui from the University of California, Irvine, this new phase of matter is akin to how water exists in different states: liquid, ice, or vapor. It has never been directly observed before, making it truly groundbreaking. If we could visualize it, Jauregui says it would emit a bright, high-frequency light. The researchers achieved this by placing a mixture of hafnium and tellurium under an extremely powerful magnetic field of up to 70 Tesla, a strength far beyond what a typical refrigerator magnet can produce. This intense field transformed hafnium pentatelluride into a spin-triplet excitonic insulator, effectively halting its ability to conduct electricity. This discovery opens up exciting possibilities in information technology. Instead of using electrical charges to transmit data, as current computers do, spin-based electronics could potentially use spin states. This shift could lead to more energy-efficient computing solutions, including self-charging systems that are crucial for long-duration space missions. Jauregui elaborates, if we can develop computers that use spin instead of electrical charge, it could revolutionize space exploration for missions venturing deep into space. Where radiation poses a significant threat, this new technology could ensure that computers remain functional and operational. But here's where it gets controversial. Could this breakthrough also have implications for quantum computing? While the immediate focus is on energy efficiency and radiation resistance, the potential for quantum devices is enormous. Some experts argue that harnessing spin states could unlock new realms of quantum computation. Though many challenges remain, the study, published in Physical Review Letters, marks a significant milestone in materials science and quantum physics. As researchers continue to explore the properties and applications of this new quantum state, we may be on the brink of a technological leap that could transform both earthbound and space-based computing. So, what do you think? Is this the future of computing, or just another fascinating step in our quest to understand the universe at its most fundamental level?